Hi everyone, I hope you're doing great. My name is Farid Barasta and I'm going to explain a little bit about techno-economic analysis of wind-powered ammonia and hydrogen production in Newfoundland, Canada. The aim of this research is to evaluate the potential of wind to hydrogen and ammonia project for two prospective sites with a 7.5 megawatt wind turbine by calculating the levelized cost of electricity, hydrogen, and ammonia. The prospective sites are located across the Newfoundland province of Canada. During the next slide, we will be looking at how to model this system. Based on the wind resource assessment and turbine characteristics, which includes a cutting speed, cutout speed, rated speed, top height, rotor diameter, and rated power of turbine. The annual energy production were estimated in both sides. According to the result of the paper, which was presented in IEEE conference, which was held in St. John's, Newfoundland in November 2023, the total annual energy production for Enercon wind turbine, whose capacity is around 7.5 megawatts. In St. Anthony, in Stephenville, they're around 21,500 megawatt hour and 26 around 26,000 megawatt hour respectively. This indicates that the type of wind turbine plays an important role in annual energy production. The Haber-Bosch process conventionally are reliant on fossil fuels, so this process can be adapted to use wind power for sustainable green ammonia production. In this process, nitrogen is obtained from the air and hydrogen is generated through the electrolysis of water. In the sustainable approach, for separation of nitrogen from the air and splitting the hydrogen from the water, and also desalinating seawater, wind energy can be used to power these processes. In addition, the nitrogen and hydrogen are then combined in the presence of a catalyst, typically iron, to form ammonia. The use of wind energy as an energy source to provide essential conditions include maintaining a pressure of 300 bar and operating at a temperature of 500 Celsius degrees can make the ammonia production process more environmentally friendly. The right figure illustrates the process of green ammonia production and also the configuration of each subsystem within production facilities. Wind energy is converted into electricity through the wind turbine. The electricity is then used in various stages of the green ammonia production. First, this electricity power the desalination unit to remove salt from seawater in order to produce desalinated water. Associated amount of electricity consumption is around uh, 40 kilowatt hour per ton of ammonia. Next, in the electrolyzer, the electricity is used to generate hydrogen. This process is the most intensive process compared to other processes. and is equal around 11,000 kilowatt hour per ton of ammonia. Then, by the use of compression system, hydrogen is pressurized and stored in hydrogen storage tank. These energies equal around 240 kilowatt hour per ton of ammonia. Additionally, the electricity is directed to the air separation unit to produce nitrogen from the air. The required energy in ASU unit is around 90 kilowatt hour per ton of ammonia. In the ammonia synthesis unit, around 300 kilowatt hour per ton of ammonia is used to facilitate the synthesis of ammonia. Lastly, the electricity is used in order to pressurize the ammonia in ammonia storage tank. The amount of electricity for the storage of ammonia is negligible compared to other items in this study. In this calculation, the energy required by the electrolyzer is assumed to be around 54 kilowatt hour per kilogram of hydrogen for a PEM electrolyzer whose capacity is around 100 kilowatts. Levelized cost of electricity for the sites located in Saint Anthony and Stephenville are presented in the left table. Based on the result of the calculation, the levelized cost of electricity for the location of Saint Anthony is 106.5 US dollar per megawatt hour, while the levelized cost of electricity in Stephenville is 129.5 US dollar per megawatt hour. This shows that establishing the wind turbine in in Saint Anthony is more viable than Stephenville in terms of levelized cost of electricity. According to the right table, levelized cost of hydrogen is around 7.6 per kilogram of hydrogen for Saint Anthony and around 8.9 US dollar per kilogram of hydrogen for Stephenville. These figures provide a real insight into the economic consideration for hydrogen production in these specific regions. In addition, these figures have a huge gap with the target price of 2 or 3 US dollars per kilogram of hydrogen. According to the breakdown pie chart, the contribution share of electricity in levelized cost of hydrogen in Saint Anthony and Stephenville are 79% and 82% respectively. So we can conclude that in both cases, more than a three-quarter of the levelized cost of hydrogen is attributed to electricity. This shows that the cost of electricity plays a crucial role in determining levelized cost of hydrogen. Sensitivity analyses were conducted on levelized cost of hydrogen by varying electricity input price and capacity factor to understand their impacts on levelized cost of hydrogen. According to the diagram, an increase in the price of levelized cost of electricity results in a substantial rise in levelized cost of hydrogen. Conversely, an increase in the capacity factor from 20% to 55% lead to a decrease in levelized cost of hydrogen. This is the reason why using wind turbine in areas with higher average wind speed is generally more financially viable than in areas with lower average wind speed. As a conclusion, in order to compete with gray and blue hydrogen, a reduction in levelized cost of electricity is necessary. A financially viable scenario was pinpointed with a levelized cost of electricity, which is equal to 40 US dollar per megawatt hour, which results in a levelized cost of hydrogen, which is equal to 3 US dollar per kilogram of hydrogen. Optimizing the levelized cost of electricity component is crucial for achieving economic feasibility in hydrogen and also ammonia production.